Okay, next we have Tim Klinger. Tim has been leading work and learning at IBM Research. Among other things, he has made important contributions to multitask learning, natural language understanding, and recently fundamental advances in compositional generalization, where he's been leading work at IBM. Take it away, Tim. Oh, you're muted, Tim.
Thank you, Alex. Let me share my screen. Go full screen. There we go. Okay, can you see my screen?
It says it's starting to share, at least for me.
Yeah, same here.
Okay. Sharing yet?
Nope.
It says I'm sharing. Says I'm sharing.
Stop sharing and share again, Tim.
Okay. Anything?
Nope.
No, please send your slides to me. Oh, okay. Now we can see it.
Yep.
Now you can see. Okay. Great.
Fantastic.
So I'm going to talk today about compositional generalization for machine learning models and an approach that we developed called compositional program generation. And I'll explain what all that means. And this is joint work with Luke Liu, who's a student at NYU, and the folks that you see here who are at IBM. Okay, so probably a lot of people have heard this term, but I'm not sure that everybody knows this who might be on the call. So let me explain a little bit about what we're trying to do and why. The question is, what is compositional generalization? So we have a machine learning model that we're training on some training data, and we want that model to generalize in two important respects I'll describe. But first, the setting where we can talk about this is a setting where the input domain of the task has some notion of wholes and parts, some notion of composition. So an example of this would be language, where say translation of one sentence in one language to a sentence in another language. In language, the words are the primitive constituents, and you can combine words into phrases, and you can combine phrases into larger phrases. So it's a natural domain in which you could talk about this. Another domain where you could talk about this is in understanding scenes, where you have objects and relations between them, and each object might be constituted by other objects. So that's the thing that you should think about when I'm talking. Those are the natural applications for this topic. Okay, so the key concepts. What is compositional generalization? Two things really, and these terms come from linguistics, so if they're a little bit strange, it's because they were originally introduced in the linguistic context. So the sorry, hang on one second. Sorry, landline call. Okay, so you have productivity, which means that you would like your model to generalize to usually longer inputs than it's seen in training, but could also be shorter inputs. And this is natural. Like if you're doing something with language, there shouldn't be any sort of arbitrary cutoff in the length of sentences that you're dealing with. It should understand for languages that are infinite what the sort of recursive structure of the language is and generalize to longer or shorter inputs. The other concept is something called systematicity. And what that is you'd like your model to generalize to inputs whose parts are of the same type as the parts that you've seen on inputs during training. So it has the same, so you've seen the same types of parts. And an example of that would be, this is an example taken from the scan data set. So the object here is to translate these sentences like walk left twice into a sequence of commands that are capitalized version. that could be executed by a robot in order. So walk left twice turns into turn left, walk, turn left, walk. And similarly, run left twice turns into turn left, run, and look left twice turns into turn left, look, turn left, look. And by this point, you're looking at this and saying, I get the pattern here. The general pattern is there is some class of parts. This is the first word here, walk, run, look, that's in some class of actions. So maybe it also includes jump, flip, twist. And no matter what the actual word is, what you want your model to do is to take that action in context, action left twice, and turn it into left A prime, left A prime, where A prime here is the translation of that action into the target language. So for example, walk gets translated to capital walk. So there's this is this abstract rule that is sort of defined at the level of classes that we would like the model to discover so that it doesn't need to get trained on all the possible combinations of words in these classes. And interestingly, this type of problem is one that presents problems for standard neural models. So if you take a transformer or you take a recurrent neural network of some sort, chances are if you give it jump left twice, it will not output left jump, because it just doesn't find this pattern. The question is, but yet it's very natural and we all see it. So what's going on here and how can we make a model that can do this? And that's the question of systematicity. So two things, productivity and systematicity are the key goals. So what we're trying to do is build a system that generalizes this way, productively and systematically. And we're focused on a sequence-to-sequence language setting. So you can just think of these types of problems that I just showed you, language to language, sentence to sentence. And our goal is to show that whatever we do, obviously we have to get strong accuracy. We're looking for state-of-the-art accuracy on benchmarks that test this. And I'll show you. So obviously you want state-of-the-art accuracy, but also the promise of this approach is really sample efficiency. So by generalizing strongly to rules that are defined sort of at the meta level with respect to classes, you want you hope to get something. What you hope to get is not having to train on all the possible combinations of the elements of each class. So you would expect that if you had a model that does this, it should be more sample efficient. It should get to strong accuracy more quickly than models that don't do this. So that is really our test. And finally, we're interested in understanding these concepts more deeply theoretically, but I won't talk more about that in this talk, but we do have some work there. Okay, so that's our goal. We hypothesized that there are three key ingredients, okay? Modularity, abstraction, and compositionality. These are the three ingredients that I think you need in a system that wants to do this. And I'll explain next what these mean more specifically, but just keep this in mind as a high-level hypothesis about what's required to solve this problem, to solve machine learning problems in a systematic way. So before I launch into all to the model that we use and all the details, I want to just show you the motivation here, how we're capturing what we're doing in a more theoretical way or a more formal way. So there's a notion of something called a compositional function, and this is a different notion than the usual idea of compositionality that F is composed with is G composed with H. This is a relational notion that says that the meaning of the whole should be a function of the meanings of its parts. So meaning here comes from linguistic literature. It really means our model. Mu is our model. And what we would like for our model is that when we apply it to a whole thing, it's a function of the meanings of the parts of that thing. So we need a notion, as I mentioned before, every domain needs a notion of wholes and parts. And here, the parts are U1, U2, UN, and wholes are formed by, and this is a definition, this is a notion that comes from Pagan and Westerthal that we adopted here. I give the reference here. We have abstract grammar rules, alpha, that are used so that every expression in the input language that we care about is formed by applications of these rules. So here I'm making a whole, an alpha whole, by applying it to the parts U1, U2, UN. And what this is saying is that the meaning of that whole is a function, R of alpha, of the meanings of the parts mu of U1, mu of U2, and mu of UN. So the interesting thing here is the function part, this semantic function R of alpha. So what you'll notice is that really this is a function that depends just on the rule that you're using to make a whole from the parts. So R of alpha you can think of as a kind of a module. It can be a different function. Yeah, it does look like. So there can be a different function for each rule alpha. And this is important. So a monolithic model like a transformer, for example, would not be able to wouldn't have different functions here. There's just sort of one function, just the network. But what this is saying is, no, there are modules that can be different. And it's important that they're different because honestly, the reason that you're making wholes out of parts is because they mean something to you and they mean something perhaps different than each other. So it makes sense to really have distinct modules for different types of rules for constructing things. And that's what this definition provides. So just to get back to my original hypothesis, the three things that are operating here are abstraction in the form of these abstract rules alpha, modularity in the form of these different modules for each rule, R of alpha, and then compositionality, which is this relation between the meaning of the whole and the meaning of the part. So our architecture is based on this understanding of the problem. And now I'll show you, let's get into more detail. So, okay, so our approach, what we want to do is, remember, we're doing sequence to sequence problems. You have an input. In our case, we supply a context-free grammar of the input language, and we generate a parser. So we're able for each input to construct an abstract parse tree. And I'll just flip ahead for 1 second. If you look on the left of this diagram, it shows you what such an abstract parse tree looks like. There's rules, alpha, beta, gamma, delta, epsilon, iota, and they apply to the words, and they parse the words into abstract types, T1, T2, T3, T4. This is what we're looking for from an abstract part type hierarchy. And what we're doing is what's in the CPG box, the CPG theta box. This is where things get learned. This CPG theta is generating each input that's aligned with the parse. And it applies that semantic function to a dictionary translation of the input to get the output. So this, the whole structure of this is look at the input, figure out what its part types are, and generate a sort of custom bespoke semantic function that when you provide it with the translation of the input, this dictionary provides the translation of each word in the input to its corresponding phrase in the output. When you take the semantic function and apply it to the translation of the words, for example, like little walk goes to capital walk, then you get your output. And I'll show you how this implements the idea that I just presented. But these are the three main parts. In these parts, we're learning, in some cases, we're learning the dictionary. In some cases, we're providing the dictionary. And we're providing the context-free grammar and generating the parser. So what's really being learned here is CPG theta. CPG stands for Compositional Program Generator. And obviously, it's called compositional because it's going to build up this semantic function compositionally. And I'll describe how that works in the next slides. So let me run through an example before going into a lot of detail. I'm just going to show you the big picture of the inference procedure. This is how we go from the input, which is on the lower left, to the output on the upper right. And this is from the dataset scan that we've been talking about. And so let's go through it step by step. Let's take it step by step. That's for the language models that are listening. So you have initially you have a dictionary mapping. Each input term, jump left and twice to its corresponding term in the output. So jump just gets mapped to capital jump, left gets mapped to capital left, and twice actually gets mapped to nothing, the empty list, and I'll explain where twice the semantics for twice come in. But this is to provide the input to the semantic function that we're going to construct in the next two rounds. So in the case of scan, we're learning this dictionary. In the case of COGS, which is the other data set that I'm going to talk about, we're providing it, but we think we could learn it as well. Okay, so step two, we apply another grammar rule. So in this case, we recognize that T1 followed by a T2 is a T4. That's what the rule delta tells us. So the way to think about this is that the phrase jump left is an example of the type T4. It's in the type T4. So we already have our dictionary translation. So now what happens is that we've applied this rule delta, and we need to build a corresponding node in our semantic function that we're going to apply. And the node consists of two parts. First, there's a concatenation. So we take jump and left and we concatenate them. And then there's a symbolic copy operation, which is parameterized by a distribution that depends only on delta. So what I mean by that is there's a set of private parameters for this distribution, p theta, private to this rule, delta. And this distribution characterizes the order in which we want to copy the elements from our sequence, jump and left, to the output. So in this case, it's zero index. So in this case, copying one is left, and then zero is jump, results in the output left jump, which is the reverse of jump left. And so every operation for scan is of this form, concat followed by a copy. And exactly what gets copied where is determined by this probability distribution that depends only on delta. So in particular, this probability distribution, it does not depend on the input and cannot overfit to the input. It depends on the input. It doesn't depend directly on the input. It only depends on the delta. So anytime we see a rule delta, we will use exactly the same example from, and we will use the same copy program, which is a fixed symbolic program that depends on this distribution to produce the output. And we can go another layer. So finally, we get a rule that says if we have a T4 followed by a T3, we get a type T5. That's the rule epsilon. In this case, we do a concatenation again to get, and we're concatenating left jump with the empty list. So we get left jump again. And we're doing another copy. So we're sampling from a distribution that's local to the epsilon rule. And in this case, the sample is 0, which corresponds to left, then 1 corresponds to jump, then 0 that corresponds to left, and 1 corresponds to jump, and that's the output. So if you look at the final, here's just to flash the final picture again, this is what the whole thing looks like. This is what the whole inference process looks like. And you can see, sort of stepping back, what we've done is we've used this parse, this abstract parse, as a scaffolding to build the structure of the function, which is composed of these probabilistic symbolic programs that are parameterized by these rules. So it's in alignment with the abstract rule, and they're composed in exactly the same parallel structure to the abstract parse of the input. And that's it. So that's what scan looks like. We benchmark in compositional generalization. So COGS requires semantic parsing, which means translating English or English-like sentences into a logical form. And here's an example. Emma ate the bread gets translated into, there is some object 3, which is a bread, and the agent, which is the subject of the eat event 1 is Emma, and the subject, and then the theme or the object of the eat event 1 is the bread 3. So this is the sort of general form of these. I won't go through this in a lot of detail again, but The difference between the setup here and the setup for the very simple scan is that here we need each node to have two parts to it. One is an expression, which is going to be the output that was required, the star, bread 3, etc. And the other is the set of objects that are available at that point in the tree. And instead of learning copy operations, we just learn very similar substitution operations. So we substitute these objects into flots, which are denoted Y here. So for example, for the verb eat, we know we have a subject and an object. Other verbs are different. Some verbs don't have objects, some don't have subjects, some don't have indirect objects. So each one has needs a different sort of template here. This is the one for eat, and this substitution that we sample from the rule directs the substitution of these object variables into the Y slots. So you can see that after substituting according to this substitution template, we end up with some of the Ys replaced with some of the objects. And otherwise, it proceeds exactly the same way recursively up the tree to produce the output at the top. So these are two different setups that have the same general form that use very basic but simple operations, copy and substitute. And I won't go into I won't provide the details of those during the talk, but I'll put them at the end. So if you want to look through and see exactly what this inference procedure looks like and what the copy and substitute operations look like, you can look there. Okay, so I mentioned the dictionaries. Where do those come from? So the scan dictionary is just as I mentioned before. This is sort of very simple mapping from the lowercase run to the uppercase run. The actual data set requires this I underbar here. So you can see the mapping is quite simple, and we are able to learn this jointly with CPG. The COGS dictionary is more complicated and it requires these different abstract expressions, these sort of templates with slots in them for each different type of verb, because the different types of verbs correspond to really different metadata. Some require agents, some require themes, some require recipients. These all correspond to subjects, objects, indirect objects, etc. So the initial values for these for this dictionary is supplied in this form, and then it figures the rest out. So that gives you a sense of what the dictionaries look like. So let me talk a little bit about the experiment, the model and the experiments and what we're trying to do. So we're training on these two data sets, SCAN, which was one of the first benchmark that was used for testing compositional generalization, and COGS. Now, SCAN has two splits. One, the length split is to test productivities, longer and longer lengths, and the other is the add jump split, which tests for systematicity. So what we did was we of course evaluated on the original data set. So those would be called classic, COGS classic, SCAN classic. But we also created few shot and what we called extreme few shot versions of these data sets to be able to test our few shot capabilities in this model. So the way the few shot data set was created is we sorted the original data set by length, and we looped through, and we parsed each input sentence from the instance and rejected any that had the same parse as one we've already seen. So we're basically removing duplicate parses. If you do that, you get down from 16,000 to 743, while still maintaining complete coverage of all of the types in the grammar and all of the possible parses for the instances in the data set. If instead of removing filtering out the ones that have the same parse, you filter out ones that have the same type as a type that you've seen already, you actually get down. So you're just disallowing anything. You might have a distinct parse, but it's using the same types that you've seen in some other parse, then you would reject it. In that case, you get down to just 14 examples out of the 17,000 for the length split. Similarly, for the systematicity test, And for COGS, it's even more sort of dramatic. So if you do this it in this way to just 22 that kind of cover all of the different types that are represented in the data set. So this is what we're going to evaluate the model on. And just to give you a sense of what these look like, here are the extreme few shot data sets. You can actually put both of them on one page. And it won't be possible to look at these in detail now, but if you want to go back later and look. One thing I'll point out is that these really, really are hard because, for example, in COGS, the longest sentence here is, I believe, 8 tokens or 9 tokens, and the longest sentence in the generalization set that it has to generalize to is 55. So there's really, it's really quite extreme. But these do cover all of the syntactic types in the grammar. So, okay, model and training. As I mentioned, we maintain separate modules for each probability distribution associated with the rule. So all of the p theta of alpha, delta, epsilon, etc., are all separate modules that don't share parameters. These modules are implemented as really simple one layer feedforward networks in the case of scan, or a 2-layer feedforward network in the case of COGS, followed by something called a Gumbel softmax estimator, which is a way of getting a discrete sample, which is what we need to map, for example, in copy when we get the indices that we want to map the input to. They need to be discrete, and this is what Gumbel does for us. The objective is just to minimize the cross entropies, the usual objective for argument of theta of the expected cross entropy of CFG against the ground truth, y. This is just a standard way of comparing sentences. So training is interesting. Training is done in a curricular way. So we group input by input length. So we group either two to three input lengths together, and we only move to the next stage of training when the stage accuracy reaches 1.0 perfect. When that happens, we freeze the rules. We freeze the module associated with the rules that were learned in that stage, so it doesn't forget, and it's able to reuse those modules in types that occur when longer sentences are seen in later stages. So typically the types kind of increase as you go because you need more types to represent the concepts in longer and longer sentences until you reach some kind of fixed point.
Can
so
I request you
it's
to
really okay, sure, yeah. So anyway, let me skip forward and show you some results. Okay, so here is the classic scan, the original data set. The top is test, the bottom is training curves, and the left is length, the right is adjunct. So the left is productivity, the right is systematicity. So if you look at the top,
Tim, I'm still seeing your last slide for some reason. I don't know if it's the same for anyone else.
I forwarded it. My machine might be slow.
There we go.
Now we can see.
Okay. Okay, sorry. So make a long story short, what we're seeing here is 5 different runs for each of these splits, and the top is showing test. So so you can see that there's the variance tends to be when it starts to learn, but not so much the shape of the curve. So it really does learn very consistently. In some cases, it takes longer to find the solution than others, but there's not much variance in the curves. This is the same is true for both length and adjunct. What you see in training below, these little drops here are where this is showing stage accuracy. So it's showing you kind of where you start a new stage and you move on, you start seeing new sentences that it has, new types that it hasn't seen before, and it has to start learning them. So those are the learning curves for each stage, but eventually it does get up to 1. Show you one last thing here. This is so COGS. This is kind of maybe the most impressive result, or the most striking result is this is COGS, which is a very difficult data set, on the extreme few shot training data set of just 22 sentences. And here what you see is the same pattern. The left is training. You see the same pattern of increasing competence for each stage. And on the right, you see test accuracy. So this actually is achieves, in all cases, we get 1.0 test accuracy. But what you're seeing here is basically that it's getting to that point from having only seen 20,000 examples total. Very, very fast learner. The test curve here is, I won't go into details, but that's the main takeaway. So next steps are learn the grammar and the parser and dictionary jointly. This can be difficult because it's a non-stationary problem. They depend on each other. So let me just wrap up. The takeaway here is we have this approach, compositional program generator, that uses knowledge. It uses grammar rules and a dictionary in some cases. It form of grammar rules, modularity in the form of distinct probabilistic copy and substitution programs associated with each rule, and recursive composition, where it bottom-up constructs a program for each input. It learns incrementally, it's interpretable, gets perfect generalization on these two benchmarks, and even under a 1000x data set reduction in both cases. So that's it. Here are some references to all the things that I talked about, and thank you.
Awesome. Amazing results, Tim. Thank you. So one question, since we're past time, how complex can a grammar and vocabulary be at the present? Would it already be possible to translate a subset of English into an actual programming language?
Yeah, I think so. I mean, so to give you a sense, the COGS grammar has 60 types in it. And it covers a fairly large chunk of English grammar already. So it's recursive, it has it has recursive types, it has most of the things that it has fairly complex English sentences. You could to translate into programming languages. We haven't thought about English to programming languages, so it's just an interesting idea. The main trick would be to map the words in English to the corresponding terms in the programming language in the dictionary. So that I would have to think about how we would do. But there's nothing in principle that would prevent us from trying that.
Well, one more quickie. I'll just relay one of the comments. This looks like type theory.
Yeah.
Sorry, category theory.
It looks like category theory. Yeah, it does look like category theory. And actually, there is a paper that describes how compositionality in the way that I've described it works in category theory. There's two papers actually, and I can't remember the names of the guys, but if you contact me, I'll point you to them if you're interested in that. Yeah, category theory is a way of understanding composition, so it makes sense that category theory would apply here. And, I think it does, but I'm not sure that it helps explicate it to the average person to look at it that way.
Okay, awesome. Thank you, Tim.
Okay.
All right. Thank you. Thank you very much.
So thank you. Let me stop recording.